Biochemistry Analyzer Basic Principles. All biochemistry analyzer, whether it is a colorimeter, semi-auto analyzer or auto analyzer, use a part of electromagnetic spectrum. This diagram shows wave motion of electromagnetic radiation. Light travels in the form of wave. Distance between one peak of the wave to the next peak is known as wavelength. In short, wavelength is distance of one complete cycle. Depending upon the wavelength, electromagnetic spectrum has been divided into various regions: gamma rays, X-rays, ultraviolet, visible light, infrared, and radio waves. As we move from gamma rays to radio waves, wavelength increases from 0.0001 nanometer to 100 meter. Ultraviolet and visible part of the electromagnetic spectrum, which covers 300 nanometer to 800 nanometer, is used by the UV visible spectrophotometer or the analyzer. Color of different wavelength regions: 380 to 450 violet, 450 to 495 blue, 495 to 570 green, 570 to 590 yellow, 590 to 620 orange, 620 to 750 red. Parts of the analyzer and its function. Let us see how the analyzer works. Analyzer has the following parts: light source, filter, cuvette, detector, and readout meter. Light source. Most of the analyzer use halogen lamp as light source. Halogen lamp gives radiation in the range of 350 to 3500 nanometer. The radiation coming from the light source is selected by the filter to a narrow band of the wavelength depending upon the test. This radiation falls on the sample. Now, depending upon the concentration of the sample, certain amount of light is absorbed and rest is transmitted. The transmitted energy is converted into electrical energy by the detector. This electrical energy is read out by the meter as absorbance. This is what happens in colorimeter. We get reading as absorbance. Analyzers are more complex and expensive. Analyzers have stored calibration curve for each test. For example, let us say this sample gave an absorbance of X, and if we refer to this calibration curve, the absorbance X is going to give us a concentration of Y. So, analyzer gives us the result directly in the form of concentration. All analyzers work on the principle of Beer Lambert law. and it is represented by the following expression, where A is absorbance, I0 is intensity of incident light, I is intensity of transmitted light, C is molar concentration of compound, L is length of sample cell, epsilon is molar absorptivity. The light coming from the light source is filtered by the filter. This incident light coming from the filter is of particular wavelength. This light is absorbed by the sample. Absorption depends upon number of molecules present in the sample. Higher the number of molecules, more the absorption, and absorption is directly proportional to the concentration. Hence, absorption can be used to find the concentration of the compound. Let us say the incident light is 100% and 90% of the light is absorbed by the sample. The 10% of the light would be transmitted. The ratio between this incident light I0 and the transmitted light I gives us the absorbance. This absorbance can be expressed as absorbance equals log to the base 10 of I0 upon I. If we replace I0 and I with 100% and 10%, we get log to the base 10 of 100% by 10%. And if we work it out, we will get log to the base 10 of 10. And you know the value of log to the base 10 of 10 is 1. Hence, absorbance is equal to 1. This is the readout which would be given out by the meter. Anyway, you don't have to do all these calculations. This readout is directly given by colorimeter in the form of absorbance. Application of Beer Lambert law. Let us see how the absorbance increases with concentration. Out here, we will see the calibration curve of hemoglobin by sign methemoglobin method. This is our blank containing no hemoglobin. This is our standard containing 3.75 gram of hemoglobin per deciliter. This is our 5.00 standard. This is our 7.50 standard. This is our 15.00 standard. This is our sample 1. And this is our sample 2. As the saying goes, old is gold. This is one of the most oldest instrument I am having in the lab. So let us take the absorbance of blank first. So this is our blank containing no hemoglobin, and let us see its absorbance. Okay, blank is giving blank is giving 0.03 absorbance. So let us see the absorbance of our first standard, that is 3.75. Zero point 0.12, 0.12. So standard 3.75 is giving absorbance of 0.12 minus our blank 0.03. Let us take the absorbance of our second standard. Standard 5.0. is giving the absorbance of 0.15. 0.15 minus 0.03. Let us take the absorbance of our third standard. Concentration of third standard is 7.50. 7.50 is giving absorbance of 0.21. 0.21 minus 0.03, that is absorbance of blank. Now let us take the absorbance of our last standard, that is 15.0. Standard 15 is giving the absorbance of 0.35. 0.35 minus standard absorbance of blank 0.03. Now let us take the absorbance of our sample. Sample S1 sample S1 is giving absorbance of 0.29. S1 is giving absorbance of 0.29 minus blank 0.03. Now let us take the absorbance of our second sample. S2. So S2 is giving absorbance of sample 2 is giving absorbance of 0.43 minus 0.03. Now let us plot a graph. Now we are going to plot a graph of absorbance and concentration. This side is our concentration and this side is our absorbance. Now standard 3.75 is giving absorbance of 0.12 minus 0.03 of blank, that is going to be 0.09. 0.09. 0.15 minus 0.03, 0.12. 0.21 minus 0.03. Okay, 0.21 minus 0.03 will give us 0.18. 0.18. 0.35 minus 0.03 will give 0.32. The sample 1, that is 0.29 minus 0.03 will give 0.26. 0.43 minus 0.03 will give 0.40. Now let us plot a graph. So standard 3.75 is giving absorbance of 0.09. So that will be okay, out here 9 means okay, 1 2 3 4. It is going to be out here. Standard 5 is giving absorbance of 0.12. 0.12, 0.12, 0.12, 0.1, 0.11, 0.12. This is out here. standard 7.5 is giving an absorbance of 0.18. Standard 7.5 out here, 5, 6, 7, 8. Okay, it is out here. Standard 15 is giving an absorbance of 0.32. Standard 15 is giving an absorbance of 0.32. 0.32. Okay. Okay. The line is slowly bending out here. Which means it is slowly becoming non-linear. This is also because of the photometer which I am using is very old one, but still it is giving a good curve. Now we'll do it with a pen so that it becomes clear. Okay. Okay, now let us okay. Now let us find the concentration of our sample. So sample S1, it is giving an absorbance of 0.26. This is 0.2. Okay, 26, 0.25. So 26 is going to be out here. So if you go straight, it is out here. Okay, so if I come down, so it is coming out here. So sample 1 is giving a concentration of 11.2 gram per deciliter. Now let us see the concentration of S2, that is the absorbance is 0.40. Now this curve is not going to go straight for forever. Okay, in fact, if you see it closely, it has started deviating from here. It has started deviating from here. Out here, as we keep on increasing the concentration, the curve slowly becomes non-linear. Though you keep on increasing the concentration here, the absorbance almost remains flat out here. Sample 2's absorbance, that is 0.40, falls in the flat or non-linear region of the curve. The curve is linear out here. From here it starts deviating and becomes completely non-linear over this region. That is why every test kit gives the linearity of the test. If your result falls outside the linearity, you have to dilute the sample and repeat the test. In this case, we have to dilute sample 2 and bring its absorbance from 0.40 to the linear region of the curve. Limitation of Beer Lambert law. The law assumes that absorbance is linearly proportional to concentration, but at a high concentration, the absorbance becomes nonlinear. If the absorbance falls in the non-linear region, you have to dilute the sample and repeat the test.